There was no shortage of hydrogen that day. Electrolyzers were running, electricity was flowing, and production looked completely normal on every dashboard that mattered. If you were sitting in a control room upstream, nothing would have suggested a system-wide failure was about to unfold. And yet, across California, hydrogen stations began shutting down one after another until more than 60% of them were offline. Drivers waited hours. Some couldn't refuel at all. Vehicles designed to run on hydrogen became unusable, not because hydrogen didn't exist, but because it couldn't reach them. The trigger wasn't a plant failure or a breakthrough gone wrong. It was a single compressed hydrogen trailer incident during maintenance, followed by a safety response that grounded fleets and disrupted delivery across the network. That one event exposed something deeper than a supply disruption. It revealed how the hydrogen system actually works, not how it's described in models or presentations, but how it behaves under real-world conditions. Because hydrogen doesn't exist where it's produced, it has to move. And the moment that movement is interrupted, the system separates into two disconnected halves. Production on one side, demand on the other, with no reliable bridge between them. To understand why that bridge is so fragile, you have to start with the molecule itself. Hydrogen is the lightest element in the universe. At standard conditions, it occupies a large volume for very little mass. That makes it inefficient to transport unless it's compressed or liquefied. In most refueling networks, hydrogen is stored and transported as a compressed gas. That means pressure is not just a parameter, it is the system. Vehicle tanks typically require hydrogen at 350 to 700 bar. For hydrogen to move into those tanks, the supply must be at a higher pressure. The basic relationship is simple. Flow is driven by pressure difference. If the supply pressure falls below the tank pressure, hydrogen won't move. It doesn't matter how much hydrogen is physically present. Without sufficient pressure, the system stops functioning. That's why trailers are not just logistics. They are high-pressure systems. A hydrogen trailer carries compressed gas, often in tube bundles, at pressures that allow it to deliver hydrogen into station storage and cascade systems. It is both storage and delivery. It is the bridge between production and use. Remove it, and the system disconnects. When the trailer incident occurred, it didn't just remove one unit from service, it triggered a safety response. Other trailers were grounded for inspection. Deliveries slowed, then stopped. And that's where the system began to unravel, not gradually, but mechanically. Stations operate on a continuous replenishment model. Hydrogen arrives, is stored in high-pressure tanks, and is dispensed to vehicles. As hydrogen is used, new supply replaces it. The system depends on flow. It is not designed for long-term storage at scale. When delivery stops, storage begins to deplete. At first, this isn't obvious. Stations remain open. Some fueling continues. But pressure begins to drop. And once pressure drops, performance degrades. Fueling slows, tanks don't fill completely, wait times increase. What was a functional station becomes a constrained one. And eventually it becomes a non-functional one, even if it hasn't physically shut down. This is the moment where engineering reality overrides perception. From the outside, it may look like a temporary disruption, but from inside the system, it's a loss of pressure integrity. And pressure integrity is everything. The hydrogen delivery chain is not a single step. It's a sequence. Production, compression, loading, transport, unloading, storage, recompression, dispensing. At each step, pressure is lost, energy is consumed, and risk is introduced. Compressors raise pressure. Valves regulate it. Storage systems maintain it. And trailers move it. Every component operates under stress, and every component must perform reliably for the system to function. What happened in California shows what occurs when one part of that chain fails. Not the most complex part, not the electrolyzer, but a midstream component that connects everything else. When that connection breaks, the entire system feels it. Now move from engineering to economics, because this is where the consequences compound. Hydrogen projects are often evaluated on cost per kilogram. That cost depends heavily on utilization and throughput. The more hydrogen you deliver, the lower your cost per unit. But delivery is the key word. Not production, delivery. Revenue is generated when hydrogen reaches the end user. If delivery drops, revenue drops. But most costs, capital, maintenance, staffing, remain fixed. So when kilograms delivered decrease, cost per kilogram increases. This is not a marginal effect. It can shift a project from viable to non-viable very quickly. At the same time, user behavior responds to reliability. If drivers experience long wait times or incomplete fueling, they lose confidence. Demand becomes volatile. Utilization drops further. And now the system enters a feedback loop. Lower delivery leads to lower demand, which leads to lower utilization, which increases cost, which further weakens demand. This is how a mechanical failure becomes an economic one. And this is where most models fail. Because models assume continuity, continuous production, continuous delivery, stable pressure, predictable flow. But hydrogen systems in reality are discrete. They depend on units, trailers, compressors, storage vessels that can fail individually and affect the whole. In a model, hydrogen flows like a fluid through a pipe. In reality, it moves in batches, through equipment, under pressure, with each step dependent on the last. That difference is critical, because it means failure is not distributed, it is concentrated. When one trailer fails, it doesn't reduce capacity by a small percentage. It can trigger inspections, remove multiple units, and reduce transport capacity significantly. That reduction propagates downstream, affecting stations, users, and revenue. So the system behaves less like a smooth network and more like a chain. And chains fail at their weakest link. Now layer in safety, because this event wasn't just operational, it was a safety-triggered disruption. Hydrogen systems operate under high pressure, and that pressure represents stored energy. When containment fails, that energy is released rapidly. That's why safety protocols are strict. That's why fleets are grounded after incidents, and that's why recovery takes time. Hydrogen also introduces material challenges. Embrittlement weakens metals over time. Components that appear intact can degrade internally. Maintenance becomes critical but also risky. The incident occurred during maintenance, which is often the most vulnerable phase of operation. Systems may be partially depressurized, opened, or operating outside normal conditions. Controls are different, exposure is higher. So safety is not just a layer on top of the system, it is embedded in it. And when safety is triggered, it can override availability immediately. This brings us to system stress. Under normal conditions, the hydrogen network may appear stable. But under stress, failure, inspection, reduced transport, it reveals its structure. High dependency on discrete transport units, limited redundancy, tight pressure requirements, mechanical constraints. Scaling this system doesn't remove those constraints, it multiplies them. More stations mean more deliveries mean more compression cycles. More cycles mean more wear. More wear means higher failure probability. And because the system depends on each link functioning, failure probability compounds. So scaling hydrogen is not just about building more capacity. It's about increasing reliability across every component that moves the molecule. This is the core insight. Hydrogen is not constrained by its ability to be produced. It is constrained by its ability to be moved, under pressure, through a mechanically complex system, reliably and safely. And that changes the decision framework completely. For developers, the focus cannot be limited to production capacity. It has to include transport architecture, redundancy and delivery pathways, co-location of production and demand where possible, reduced reliance on long-distance transport. For investors, installed megawatts are not the key metric. Delivery uptime is the ability of the system to maintain flow under real conditions. Because revenue depends on availability, not potential. For engineers, the system is not defined by the electrolyzer. It is defined by the balance of plant. Compressors, trailers, valves, storage, control systems. These are the components that determine whether hydrogen reaches the user. What happened in California is not an anomaly. It is a demonstration, a real-world test of how the system behaves under stress, and the result is clear. The hydrogen network didn't fail because it couldn't produce hydrogen. It failed because it couldn't move it. And until that layer is solved, movement under pressure with reliability under real-world conditions, hydrogen will remain a system that works in parts but struggles as a whole. Because in the end, hydrogen is not just energy. It is a high-pressure logistics system. And the entire system depends on whether that pressure and everything that contains it can hold.